Guy's getting ready to go to the store one morning, and he plans a few extra minutes, right? Because sometimes the store is busy. So he goes and, inevitably he does his shopping, and he finally gets there, and of course there's a big old line, so he's waiting and waiting, and as he's sitting there, he's just wishing and wishing that he didn't have to wait in line at the grocery store, but he buys some candy while he's waiting, and so forth and so on. Okay, done with his first errand. He remembers on the way home that he has to stop by the post office and check his mail, but he gets there, and you wouldn't believe it. There is another line just waiting there. So he's there at the post office waiting to be able to talk to the person at the front, right? And it's kind of a pain. He's just wishing and wishing, gosh, this sucks, whatever. Gets his package eventually, gets ready to go home, decides, man, I'm going to take this road because I know that they're doing some construction elsewhere. And he gets there and, gosh, there's a stoplight. You wouldn't believe it. What did he have to do? Gosh, he had to wait in line again, and he's going and going and going. And turns out that night he has taking this new gal out for a nice dinner and date and all that. And for whatever reason, maybe they're high schoolers, college, whatever, but there's a big formal event, like a dance, that they're going to attend. And they get there, and they're dancing, they're having a good time. And obviously when you dance, what happens with your temperature? You get hot, right? And when you get hot somewhere indoors, what do you typically do? You might sweat, you might drink something, right? So she's there, and she goes, hey, I'm having a really good time, but I'm really, really hot, and I would like something to drink. So being a gentleman that he is, he realized that there's, the table over there with all the refreshments. There's punch, there's crackers, all that stuff. And he gets there, and you wouldn't believe it. There was no punch line.
Oh.
Right? All right. So today, that was awesome because you said something funny. I said, maybe. Was that funny? I exhaled through my nostrils. Cool. Yesterday we talked about electrical power. What is electrical power? The rate.
In which energy,
Electrical power is
The rate at which electrical energy is converted into something else. Now, doesn't matter if it's thermal, that'd be like a heater, right? Doesn't matter if it's mechanic, like a fan or something like that. You're taking electrical energy and you're changing it into another form of energy. That's all it means. Now, I forgot to bring my power bill today. In fact, I didn't really forget, but I looked on the fridge and we've already paid it and we threw it away after. So next time I get one, I'll bring one in for you. Anybody remember to bring yours from home? That makes sense. Okay, we define power as the rate at which electrical energy is converted. That's how we defined it yesterday. It's measured in what? Okay, cool. But the natural question then, and this is the last little piece, if we talked about power and we said that, well, it's just the rate at which electrical energy is converted, then it also seems to make sense, I think, logically, that we better give ourselves a nice definition of what exactly it means when we talk about electrical energy. Okay. For this, the unit stuff, are you like getting more and more okay with the unit stuff that we do? Like the more practice that you get, the more natural it becomes. There's some times where you're just going to have to do this hand wavy thing and say, here's the unit, and you can use it, because it gets gross if you try to dig in and see what that actual unit means. Ashley, if you want to go check the printer, there should be, sorry to wait until you sat down, there should be 20 of those things stapled together. It'll probably be on the top one, but I'm not sure. Ask Miss Katie or Mr. LaForteza if you don't know where it is, okay?
all right.
Cool. All right. Energy. Have we talked about energy this year?
Yes.
Okay, how do we measure energy? What unit?
Newtons.
Newtons is a force,
Oh,
not watts, that's power. That's a rate at which it's converted. It was Newton meters was one way to do it. So work takes energy. Joules. Okay, it was in joules before, right? Okay, here's the weird part about this. For energy, we're just going to look at this, and without a big idea, it's related to the power, right? Because you need energy to create power, and it's just how fast is it converted. For this, electrical companies will use this to bill you because you get charged per the amount of energy that you use. Not the amount of power, but the amount of energy that you use. Now, they're subtly different. As we look at this, we're going to get just a nice definition. We're going to say in words first, electric energy, which Einstein hooks it up because realistically energy is pretty commonly the same variable or label when we talk about it. What would you guys pick for energy? E. E. Check it out. Electrical energy. E. equals. Now, it's not MC squared if that's where your head goes right away. E in that equation is the same. But here we go. If you want to know the energy that gets used, we are going to take the power that wound up getting used to power something, is the electric power. And I'm going to use parentheses to indicate that stuff gets multiplied instead of a dot or an X. Okay, we take the power, and I'm going to hold off here for 1 second. I'm going to give us energy. We'll learn the new unit here in a second with regard to electricity. But if I said it takes 10 joules of energy to do something, let's say it takes 10 joules of energy every second that I lift this and walk. So 10 joules is how much it takes. That's the amount of energy, right? Now, if I use some amount of power, could I make that movement that takes 10 joules every second? Could I do it for 5 seconds? So that's 5 joules every second. How many joules of energy did I just take up in that 5-second walk? Too much. That was 10-second walk. 5 joules per second and 5 seconds. It's 25. Yeah, it's supposed to say back. Yep. 1 for you and 19 for me. Are you guys okay with the idea of saying, hey, the total energy was just what, like the power that you used in time, right? Now, the unit game gets weird and I'm trying to avoid it as best I can, but it turns out that if you have a power rating on something, it uses that power and that's a rate, which means if you just add the time into it, instead of saying this much per second, we just now get this much. Because if you're dividing every second, you just multiply by seconds and they're gone. Now, in the context of this electric energy and power and stuff, things get a little bit wonky just as we're dealing with it. So remind me here, how is power measured? Or what unit rather? Watts. Okay, right off the bat, we're looking at electrical energy and we're pretty much viewing it from the context of the power company selling electrical energy. A single watt of energy is not much. 1,000 of them is a little bit more. In this context, we are going to use kilowatts, kW. How many watts are in a kilowatt? 1,000 of them. Okay, in time, if you're a power company, does it make sense to measure every single second? Not directly. What's a more reasonable amount of time that you as a power company might manage with thousands of people that you're selling to? Hours is much more reasonable, right? So we're going to measure time in this context using hours, or H. And here's where we're at. Last little part. Electrical energy could be thought of as joules, just for the record. However, in this case, and this is kind of annoying, on the right side, what happens with the units? What's happening between power and time? They're doing what? So what happens between kilowatts and hours? You get electrical energy in kilowatt hours. This is how electricity is built, and it's a strange idea, but we'll dig into it. To make this make a little bit more sense, this is super easy. Energy, or electric energy specifically, is just power, P, times time. That's it. The electrical energy is just the amount of power that you're using it times time. And that's because power, remember that idea of watts, is really joules per second. So there's energy in there just naturally. This is the units that we use here. Okay, for this, do you guys remember what any of the nice measurements of joules were that we used? About 1 joule of energy, there was something that we used over and over. Dropping something. It was a tennis ball from knee height. That's about a joule. So not much, right? Now, that's mechanical and physical energy that you could actually think about. It's harder when you start thinking in terms of electricity, but I have one little conversion factor if you would like. 1 kilowatt hour, and this is just going to be a follow-up. 1 kilowatt hour of energy, of electric energy, turns out that this is 3.6, and I'm going to ask you guys to recall this. This is an old one. I very intentionally use capitals and lowercase, especially with these. I want you guys to tell me what 1 kilowatt of electric energy is equal to based on this from the board. You may need to, oh, that was much faster. Tell me how many joules it is as well. Time, don't shout it out. Think it out, I'll come check with you. Cool. Somewhere, sometime, we talked about mega showing up somewhere. Mega, kilo, centi, milli, all those things have shown up. When did we talk about that stuff? King Henry. Cool. That's very early on, like chapter 1. Check your notes, check your book. I want to know how many joules are here. Right now, if you were to check your internet speed, you're probably pulling like 100 to 500 megabits, is my guess.
Megabits or bytes? You say big?
I'd say bits. It's
My Wi-Fi makes me
so ping is awful. Depends on the server. Change your server that you're selecting. That'll fix it. Okay. Beyond that, though, a megabyte is a lot of storage or not much.
A megabyte, not much at all.
Okay. How about a kilobyte?
Not much at all.
That's tiny. Way smaller. Like a way smaller. Okay. Kilobyte, like a kilobyte, is 1,000 bits. And we're not in a computer science class. What's faster than a kilobyte speed? You're going too far. Megabyte is bigger. In fact, it's 1,000 of them. 1,000 thousands. What's that number? A million. This is 3.6 million joules. 1 kilowatt hour is the electrical equivalent of dropping 3.6 million tennis balls from knee height, which doesn't seem like a lot until you think of how much space 3.6 million tennis balls takes up. It's huge. Okay, for this, if you need it, these problems are going to be super chill, but hook it up. This helps some people, I think. Electrical energy is what times what?
Power time. Time.
Power times time. Now, this one is away from the norm. This is not standard because we change the way that we measure these. What's the unit on this one in the end, on energy? What sort of energy are we talking about? Kilowatt hours. Love it. Kilowatt hours. Okay, what's P?
Electric power.
It is electric power, and it's in kilowatts in this sense. Thousands of watts. And T? Time in what? Hours. Okay, this will work. When I look at electrical energy, and there's not many places in this class that I get my ideas goofed up, I want to have energy being a rate, so this much energy per this much time, but that's power. Okay, for these, we're going to play around with a few simple calculations just to get a little bit of practice with it, and we'll start to get a better feel for how this has worked out. Okay, any questions before we get going?
Is coulombs and ohms the same thing?
Is what?
Coulombs and ohms.
Coulombs are how we measure. It's a number. It's like some outrageous number of protons or electrons moving. Worth of charge. We talked about it. I'll come help you in a second, okay? All right. No questions? Okay. Let's get a problem knocked out, and then I want you guys to try it. And here's what I'm actually going to do. We're going to do one in our notes, and then I have some other ones that I want you to do. Do you guys have your, you don't have your text open. I want you to try this. Talk it out with one another. We have all the tools that we could possibly need for this. I want you to do 23. Cool. Yep, I'm going to leave it up here. You guys get that jotted down. I want this one in your notes. Number 23. I wouldn't believe the challenge part. Cool. Even after discussing, there's probably some issues in here. I want to make sure that if you are a person having those issues, we can clean it up and work it out. So, right off the bat, hook it up. What do we know?
We know our voltage, the current, and the time.
Voltage is 120 volts. What are we plugged into?
Volts.
What sort of outlet? Where in your house would you find this?
Regular outlets.
A standard one, not the stove, right? Okay. Now, I've commented, you don't change yours, you don't have to, but Carson, I think you're going to be able to answer this question. This drives me crazy. V equals 120V. I hate it. Carson, give me another term for voltage. It's the one that you keep giving me every time, potential difference. Just so you guys know, if you want to do it, this is what I do on mine because it drives me crazy the other way. It is entirely up to you. They're the same thing. That's how I write it. Or delta V if you'd rather. Triangle V. All right, regardless, what else do I know?
You know the current.
Okay, I know the current something is 0.5 amperes. Hey, what's here? I appreciate it. Anything else? time.
0.25 hours.
Love it. 0.25 hours. Yeah, sign out on that. Did you get that answer? Yeah.
Yeah.
Okay. Now, quick check. On your margin, just before we continue on with this problem, 0.25 is nice because you did 15/60ths. 11 minutes is how much of an hour?
I don't know.
Show me that you know how to get it other than if they're nice numbers that you can just reason out. 11 minutes. How do you figure out how many hours that is?
10 minutes and
It's 11 minutes out of how many?
60.
Ask your calculator 11/60ths as a decimal. And that'll tell you how many hours 11 minutes is. You need to make, like 15 minutes is easy, 30, 45. 0.18 repeating? Perfect.
183 repeating.
0.183 repeating. So, I'm good with that. Okay. What's 11 divided by 60, real quick? 'Cause they're like- Yep. So 11 minutes would be this many hours. 0.183 hours. I'm cool with that. 0.18 is what I would use. Okay. Anything else that we know? We have a voltage, we have a current, we have time. All right. What am I actually trying to find? The electrical energy. Can I just say E? All right. Now, this next part gets more and more important as problems get complex. This is likely going to be up on the border of the most complex problems that we see this year. I hope this isn't super stressful for you guys. You ready to do some factoring? We're not factoring. Do you guys know what it is yet? Oh, I'm so excited for the day you guys come and tell me you learned to factor stuff. All right. Man, I need equations. How do you find energy again?
P times T.
Power times time. And then this is just what I would do to help me keep this straight. Energy is going to be measured in kilowatt hours. Power is in kilowatts. And time is in hours. I would physically write that on my page because there's places where you're going to get goofed up in this problem. Now, that's all fine and dandy, I think. Have I lost anybody? Okay, write down the knowns and just write down the equation for what we're after. Now, if you didn't notice anything, the next natural thing to do is just try to do it, right? So let's just plug and chug and see how it works out. E equals, what's the power? I don't know this. Yet. We will. We will get that. Do you know the time? 0.25. So notice what just happened. We started trying to solve this and we realized that, hey, we have this equation now that has two things that I don't know what they are. I can't solve that equation. Man, if only there were some possible way to get power out of a voltage and a current. Oh, hold on. What's power? Power, electrical power specifically, is equal to your voltage times your current. We saw that yesterday. What can I get out of this? Do I have the voltage and the current? I can find the power, and not Henning, just because I spoke to you about this, I want you guys to tell me what I've done wrong. So I got 120 volts times 0.5 amps. And I'm including these in here. That's not what I'm doing wrong. What does this wind up being? 60 what? Watts. Everybody on board still? Okay. I'm going to make the following claim. Now that I have this, I'll work up this direction so I can still get to my answer. If I try to plug this back in, I seemingly have everything, right? Maybe not, but I think it seems like I do. Energy is 60 watts times 0.25 hours, right? If you do this multiplication, what would your unit be? It'd be, ooh, careful. That's the easy mistake to make. Watt hours. There's no division happening here. And I make that same hiccup in my head because I want to have it per time, but that's what power is. This much energy per this much time. What do I want that to be in? Kilowatt hours. Huh. How do you change watts to kilowatts? Divided by 1,000. Is there a fancy, easy way that you can tell me how to do that? Move the decimal where? To the Left or to the right?
Right. Wait. Oh yeah, right.
Okay, so where is the decimal in the number 60 currently? It's right there, right? 60.0. Cool. When we move it 3 to the left, we get 0.060. And what is this new unit? Kilowatts times 0.25 hours. Am I now in the right units? Now, if you didn't make that change, your number is going to be really close, but you're going to be off by a magnitude of 3. You're going to have the decimal place 3 places wrong. That's all that's going to happen. What's 0.06 times 0.25? And we're in kilowatt hours. If we're looking for electrical energy, is that what it should be? I think so. This is reasonable. Now, looking at it, this problem, mathematically, I don't think is super duper hard. I hope you guys agree that like the pure math that happens here isn't the issue. The issue is being able to recognize that you don't have everything, but you do have enough information to find it. That's always going to be the challenge in physics. Okay. Feels okay? Feels awful? Would you like to do one more together? Okay. I'm fine with that. You guys kept your homework, right? Okay, to your assignment. We got like almost 20 minutes, 15 minutes, I guess. To your assignment from last night, I want you to add, if you haven't done it yet, and I'm just going to write it all out. Last night was 6.3, right? And what were the page 158 and 159? Okay, so last night we had 18 through 20. What? 16 through 18, goodness. 16 through 18. And then 20 through 22. That's what theoretically you have either half done or completely done. What I want to do today is you're going to just add to this. You're going to hand in one assignment tomorrow. I want you to add, found on I think one more page in the text, and I'll throw them all on the board here in just a second. I want you guys to add to this, page 160. You already did these? Oh, okay. 24 through 30. Cool. 15 minutes, right meow, to get started. Page 160, 24 through 30 are the problems you're adding. Cool. I'm going to give you guys time to work now with the understanding that you're working in class means you're working. Cool. Baller. Go ahead and get started. I'll leave this not ended yet in case we have to do some more examples. And I'll get some chill tunes going. I want you guys to work on this. Questions when you have them. Cool, cool? Yes. Sign out, okay?